We're going to start with just the setup factory default. Always start with that. And then go to setup waveform generator. And we're going to go ahead and turn on a demo type signal and then switch it to edge transition violation and then turn it on. This is the signal we'll be using for this whole golden demo. From here, you'll want to scale your signal up to 200 millivolts per division. You can do that in a couple different ways with the front panel knobs with this control here, which you can click key in values. You can scroll with your scroll wheel, which is what I like to do. You can also use these buttons here and then do the same exact thing here with the time-based control. Same exact input capabilities, but I'm just going to use that scroll wheel. Again, there's also a knob, other ways to control that. And then we want to get, now that we're kind of set up, we want to jump into demo 1, which is just measurement basics. So again, very basic demo. Customer wants to dive deeper with measurement capabilities. That'd probably be a separate conversation, but what we want to do is just start with a drag and drop. So I'm going to take this rise time measurement here from the left and drop it right on the center of the waveform. Now, if you don't see this over here, make sure to click these little arrows. These are all drag and drop measurements. There's a number of them. Just hover and you can see what they do. There's vertical measurements as well. Okay, pretty cool. And then down here at the bottom, we see our results, current, mean, min, max, some statistics. Another way you can visualize this measurement data statistically is a histogram, which is pretty popular. So you go into Analyze, Histogram. Again, a lot of histogram features. We're going to jump right to the meat of it, which is switching our type to measurement and turning it on. And now we have this blue plot, which is a measurement histogram. It's a visual distribution of all these rise time measurements being made. You can see mostly it's here, sometimes it's here, and then even more infrequently, sometimes you see a very, very much slower rise time way over here, and you can kind of see that on screen 1, 2, 3. And you have some histogram data down here. And then another way you can get this information off the scope is by saving off a measurement report. So you can pop into File Save, Measurement Report. It'll create a PDF document on the scope to look at. So demo 2 is all about looking at some of the integrated tools, the waveform, the generator, the voltmeter, and the counter. So we're kind of in the waveform generator menu once to turn the signal on, but you can come back here and kind of do a more general tour. So you can come in here and select whatever other waveform type you want. You can adjust the frequency with the settings we had without adjusting the time base or anything. Something in kind of the 10 megahertz 20 megahertz range shows a sine wave, and you can mess with the amplitude, offset. I like to show adding noise, so I can come in here. Again, I'm using my scroll wheel on a mouse to do this very easily, but again, fingertip, or you can type something in, and there you go. So then whenever you're done touring through the WaveGen menu, look at some modulation capabilities. There is an arbitrary mode. There'll be a whole separate demo video on manipulating an arbitrary waveform, but make sure you get it back to demo to our edge transition violation, and then we'll close that out and look at the voltmeter next. So you'd go to measure mark, DVM, and we'll just turn it on for channel 1, and you can see down here there's a digital voltmeter. Now you might be saying, hey, things are getting a little busy here on the bottom of the screen. You can show the customer, hey, this entire results area is totally customizable. All these little bars I can drag and change the size of stuff. I can use the top bars, drag them around and reorganize them. So my measurements are kind of wide, put those there. Tuck my DVM over there, no problem. Very easy to control and get exactly how you want. But with the DVM itself, you're going to see it's more accurate than measurements made with on-screen data because it is separate hardware. You can see it's still live updating and making DVM measurements even with the channel stopped. I can turn the channel off completely and still use the digital voltmeter. And the same actually holds true for the counter. So I'm going to turn off the voltmeter and open up the counter next, measure mark counter. And I'll just quickly turn it on, counter A for channel 1. And there's, you can browse through all these different drop downs. You can change the number of digits up to 10. You can measure frequency period or totalize. And these are general purpose counters. They don't have to be on a triggered waveform. And again, you can exemplify that by stopping the oscilloscope. Again, I could even turn the channel off and this counter still works fine. The idea is if you have a spare channel on your scope that you're not actively using to visualize waveforms on screen, hook up a passive probe to it and just browse around without having to turn the signal on or scale it or trigger on it or do anything. I can browse around and make quick and dirty counter measurements or digital voltmeter measurements on a channel I might not be using. Now I'm going to go ahead and turn this back on. Now this lends itself right into our third demo, and there's 3 counters here. Might want to mention this one too. Trigger qualified. This is what our competitors have. So our competitors, you're limited to just basically counter C. We give you A and B as well. These are all general purpose. This one's a specialized counter. But rolling right into demo 3, which is update rate. If you've hooked up channel 2 to the trigger out port of the oscilloscope, you can run through this portion of the demo. Otherwise, it'll still work visually. You don't have to worry about this. This is extra credit. So let's switch the counter to channel 2, set the threshold to kind of like a volt-ish, so they're close enough. And you can see the counter now is measuring the update rate of the oscilloscope in real time because it's connected to trigger out. And so now stopping the oscilloscope breaks that, of course, because when it's stopped, it's not triggering. So you got to keep the scope running for this one. And I'm going to close this out and exemplify what this waveform would look like if I didn't have a fast waveform update rate. So thanks to our fast waveform update rate, we're kind of seeing this problem on the signal. We've been able to see it in a measurement histogram and visualize it on screen. But what if I had a slow oscilloscope, like something from LaCroix, or a Tektronix 5 series without fast ACK turned on, or even our own S series? If I come into setup acquisition, which I just did, there's this fast plot toggle box. It's on by default because there's no reason not to have it on. There's very, very few circumstances where a customer may want to turn off fast plot, but we can do it here for a demo. And now you can see my update rate is kind of in this couple hundred hertz or couple hundred waveforms per second. That problem that we were seeing on the waveform is gone. If this was the speed of the oscilloscope I was using, I wouldn't even know my signal had a fault. So having this fast plot on, you can see the faults readily visualized and seen by the histogram and on screen. And then as I knock that down, my scope's about 1,000 times slower. It's having about 1,000 times more difficult of a chance of finding that problem. So that's the importance of waveform update rate. Easy way to demonstrate it. And we'll go ahead and move on to demo 4, which is the fault hunter. So essentially what we've done so far is said, all right, there's an issue here on my signal. I've been able to do some basic analysis of my signal as a whole and some measurements and some cool built-in tools. My fast waveform update rate helps me see that this problem is here, but how do I actually capture a picture of it? And the easiest way to do that is with Fault Hunter. There's a lot of other different ways that users might try to get a picture of this problem by itself. You can sit here and try using single shot until you get lucky, but that might take you a very, very, very long time. You could go use deep memory and capture a bunch and go searching. But what I'm going to show you with 2 clicks is how the user can, no matter how skilled they are, isolate this problem. So I'm just going to go to Analyze, Quick Fault Hunter, Channel 1. And I'm going to use a little auto magic here to fast forward. But while you're talking to, while you're running this with the customer, you might explain what Fault Hunter is and does. Essentially, it's doing a statistical analysis of the waveform, and you can see it down here in the measurements. And it's trying to figure out what normal is for this waveform. And once it has a baseline of what the signal normally looks like, it can use that as a way to look for things that aren't normal, aka faults. It'll look for glitches, runts, and slow edge speeds based on what an edge speed normally is, what a pulse normally looks like, what the highs and lows of a signal normally are. So I'm going to go ahead and fast forward as we run through all the tests, and I'll meet you at the end. All right, so Fault Hunter found a couple failures. It found a slow rising edge and a slow falling edge, which we could have deduced thanks to the fast waveform update rate. We kind of saw that happening. But we're going to go ahead and take it a step further. So we can rerun that test if we're not quite sure about the results. We can view that failure. So it actually saved a waveform. When it found that failure, it saves it and caches it for you to view later. And then you can also click Copy to Trigger. So I'm going to jump straight to that. And one thing you also might note is that you can run this test per minute, an hour, 8 hours, 2 days. So no matter how rare your fault is, really good chance this will find it. I'm going to go ahead and copy the slow rising edge to a trigger condition. Boop, copied, and then close out. And what you can see here, if we go up into our trigger shortcut and click on it, it's automatically set up an advanced in this case, edge transition trigger with a time threshold, a bunch of other stuff. This would normally be like a 5-step trigger to set up with a bunch of measurements you'd have to make. Fault Hunter did all of that for you. So you don't have to be an oscilloscope wizard in order to jump to the next step of debug, which is to trigger on the waveform. And what's the benefit of triggering on the glitch and of the fault here? So if I click run and start running the scope again and zoom back in, you can see now I'm only exclusively triggering on slow rising edges. Now, to jump essentially back into demo 3 for a second, we can actually control the counter to see how often this slow rising edge is happening. So I can come in here to counter A, I can just click on this little gear to jump into it, and I can use the trigger qualified counter now. I'll turn off counter A, and then I've got a lot of stuff here on screen, so 45-ish kilohertz. That's the frequency of the slow rising edge. That's how often it's happening. Pretty cool to know. Another potential helpful tip for the user to try to diagnose the problem. And then the next thing you can actually show is the built-in history and segmented memory. So this is demo 5. So we'll start with the history mode. Pretty easy. So you just click stop, and down here with this little clock, you can come down here and navigate through the past 1,000 captured faults. And what I can actually do here is say, reset this back to fault number 1 in the history mode and just click play. And it will play through all 1,000 of these events. Now, there's also segmented memory. So if I rerun the scope and get it going again, I just go to Setup, Acquisition, and then in here you switch your mode to segmented. And in this case, we can do a couple thousand segments. Let's do 5,000 or so. And then I'll come back here and click Run. And in this case, if I bring this over here again to optimize our screen real estate, we have 5,000 of these trigger conditions that have been saved as segments, and each one's time tagged. So we can see exactly when it happened in reference to the very first segment, which is 0. So 20 microseconds later, 40 microseconds later, we can see essentially the frequency of this slow rising edge. And go back and review, and I can export all of these off the scope, etc.